This pre-class video is about chapter 3 on two-dimensional kinematics, and it talks about orbiting satellites, a bicycle rounding a curve, a swimmer diving into a pool. There's something about a puppy chasing its tail. There's also, I think this video at the bottom of this first page is something you can skip. It's, I would say it's rather overproduced and filled with way too much music and just athletes become heroes. It's just a very obnoxious, distasteful video, in my opinion, almost borderline offensive. But okay, so the actual chapter 3.1 starts to get into, they have a little analogy of moving around a city. So we are going to be setting up an x-axis and a y-axis for two-dimensional motion. Now, real motion in real life is in 3 dimensions, but we don't often get into three-dimensional motion in this course. We will a bit, but this chapter, what we're doing is only considering motion that happens in a plane, and so meaning that like north, south, east, west, like a horizontal plane, or sometimes in a vertical plane, where the y-axis actually points up. So these first talk about horizontal plane motion. So you can imagine walking some blocks east and some blocks north. You can set up an XY axis. They define, I think, plus X to be in the east direction and plus Y to be in the north direction. And there's something about, you know, if a helicopter flew that distance, you would use the Pythagoras theorem to find out how far the helicopter traveled. So hopefully you're familiar with this kind of math. Independence of motion is, well, it's not very clear what they mean by horizontal and vertical components of two-dimensional motion are independent of each other. I think all they mean there is we're going to get into Newton's second law, which says that the acceleration is caused by the force. Well, it turns out that what that means in terms of 2 dimensions is that the x part or the x component of the acceleration is only dependent on the x component of the force, and the y component of the acceleration is only dependent on the y component of the force. So you can kind of split these two things up when you're doing your analysis. There's a PhET exploration called Ladybug in Motion. Let's check that out. And you can kind of drag the ladybug around and move him around the place, or he stops, you can give him linear motion, and you can see that the velocity vector is in the direction that this bug is moving. And here he's leaving a trail of breadcrumbs behind him. Oh, he bounced off the wall. Now he's moving back, so his velocity vector has reversed. You can also put him into circular motion, and you can see, yeah, well, there you go. The velocity is always sort of on a tangent to that circular path. So at any moment, this is the direction that the bug is going, but since he's turning, he's constantly changing his velocity. So, and then you can put him back to linear. Boom! As soon as you take off the circular motion, he just continues a straight line at this constant velocity until he hits something. He bounces off the wall. Okay, so the other thing you can do is show his acceleration vector. So for linear motion, he doesn't have any acceleration unless I actually turn to manual and grab him and accelerate him in this direction. So if you now do circular motion, what does that look like? Whoop. Now let's not forget the velocity. So remember, the velocity is still tangent, but now his acceleration is to the left of the motion, which is kind of cool. It's always towards the center of the circular path. And as soon as you take off the acceleration, whoop, he just goes off in a straight line. Section 3.2 is on vector addition and subtraction graphical methods, and then section 3.3 will be on components. But basically, the idea here is when you have scalars, which are normal numbers that you're used to, you can use a calculator to add them up. But vectors are not like scalars. You don't just add them on a calculator. You have to think about what they're doing here. So they give this back again, this example of 9 blocks east. If you take that as a vector and add it to 5 blocks north, you end up with this diagonal. So, and there's something called the head to tail method. For any vector, we call this arrowhead the head, and where it starts, we call that the tail. And so you can, I think you should read through what the head to tail method is, but you're just, rather than leaving them both starting from the origin, you're shifting the second vector over. And then the sum starts from the original vector, the tail of the original vector, to the head of the second vector. So there's a whole process there. You can add multiple vectors. They also go through and prove, so that's A plus B plus C. They change it around so that first they do C and then A and B, and they find out that it's the exact same resultant vector. So this is called, vectors are commutative. A plus B is the same as B plus A. You can switch the order that you add them. You still get the same thing. There's also something called vector subtraction. And the way that works is you add the negative of the vector. So A minus B is A plus negative B, where negative B is B, but flipped in the opposite direction, 180 degrees. So they tell you how to add or how to subtract vectors. Or you just add the minus. And I think lastly, they talk about multiplying vectors and scalars. So you can always take a vector and multiply it by a scalar. What that does is it changes the magnitude of the vector without changing the direction. So like if the magnitude is, I don't know, 3 meters per second or something, and you multiply that by 4, then you get 12 meters per second as the new vector, but in the same direction. Unless you multiply by a negative scalar, and then it flips the direction of the result. Okay, and there's another PhET exploration. Let's look at that. You can either use this sort of trackpad thing down here to select position R, or you can, I guess, press reset and select its velocity V. So it starts with 0 velocity. If you want to make it go, you drag this arrow. It stops when the velocity is 0, and you drag it wherever you want to go. So if you want to go to the finish line, you can go like that. Whoop, goal. And of course, they have all these different levels. You can add, I guess, boundaries. There's something called certain death. Let's see if we can do it. So we'll reset. Now, the real trick, and I don't think anyone's going to be able to do this one, is acceleration. And this is like you're kind of giving it force. Like it just coasts. It wants to coast all the time. And you have to either put the brakes on or put the gas on. Your arrow, it's very hard to do this. Obviously, I suck. And of course, getting it to the finish to stop is just about impossible. Because it's like you have to lunar rover it up, and of course you overshoot. It goes off. Okay, don't waste too much time on this, guys. Let's move on. So while the last section, 3.2, was about vector addition and subtraction using graphical methods, this section, they call it analytical methods. I call this using components. And this is really the best way to add vectors in this course. Just use components. It's so much easier than doing all this head to tail stuff. And so what components are is anytime you have a vector, you can always, what we say is separate it into its x and y components. So what that means is that if you've got a vector A on a diagonal here, ax plus ay is the sum, where x is in the ax is in the x direction, ay is in the y direction, and they add up to be that vector. So ax and ay are called the x and y components of A. This is how we do things in physics, so this is a really important section to figure out. So I guess here we start with the helicopter path, and then we say, well, there's the component that's the east component, and the component that's the north component. Sometimes you know the x and y components. In that case, you can figure out what the magnitude of the vector is using Pythagoras. You can also figure out what the angle is by using trigonometry here. The angle here is 10 to the minus 1 of a sub y over a sub x. It's best to just draw a diagram here and figure it out. Now, if you want to add vectors, you just add the components. And this is the real beauty of the whole method. If you've got A and B and you want to add them, forget about doing all the head to tail. All you just do is you say, if R is A plus B, then Rx equals AX plus BX, and Ry equals AY plus BY. It's as simple as that. You just add the components and it all works out. So that would be, I mean, they've made it look about as complicated as they could make it look here, but it's actually quite simple when you do problems. If you've got two vectors, you know they're supposed to add together. First step, take your vectors and separate them into their x and y components. Second step, just add the components. If they're negative, then you have to subtract them out, but it's pretty easy to keep track of the plus or minus signs. Then, when you've got the components of your result, all you do is you can, if you want to get the magnitude and direction, you can use Pythagoras and the tan to the minus 1 to get that direction back. So there's one more PhET exploration. Let's take a quick look. Okay, so this is just showing you actually how vectors work here. So here we have a vector called A, and it shows you up here as you move it around the magnitude of A, looks like 22.4, theta, which it seems the way they've defined theta here is it's being measured counterclockwise away from the x-axis. So there's 90 degrees, there's 180 degrees. And actually, if it's negative, then they're talking about, so there's minus 90. Again, that's the same convention. Positive angles, I think, mean clockwise away from the x-axis, and negative mean, this other direction. So, and then there's the x and y components, and those are easy to see. If I put it right here, the y component is a sub y is 10. The x component is 20. So, and if you put it over here in this quadrant, you've still got a y component of 10, but now you've got an x component of minus 15 or minus 20. If you put it over here, then both the components are negative. Ax is negative 20, ay is negative 10, and over here you have a negative y component and a positive x component. So that's one vector. You can then take another vector. We might as well attach that tail of that to the origin as well. And now you can make a sum by adding them up. And so we could put the sum there, but so now as you change around either of these vectors, there's a plus b is equal to s. And you can also see if you click on the components here that as you change, I guess, let's say that a has some y component of 5 and b has some y component of 5 as well, then s is going to have a y component that's 10. You just add those. Or if you put it down here, the y component goes away if you have a plus y plus 5 minus 5. So the components add to give you the sum vector as well. Section 3.4 on projectile motion. So I'll just tell you a personal story. I think my high school teacher was a little obsessed with projectile motion, and so I sort of had a bad experience with it. So it's not my favorite section in the book, but it's okay. So it's basically just two-dimensional motion for a special case when there's zero x component of the acceleration and there is negative 9.8 is the y component. So, and of course, so it's basically if you have a soccer ball going along and you neglect air resistance or the forces from the air, then this is how you work it out. So, and again, there's independence of these two coordinates. So the horizontal motion, basically there's no x component of gravity, so there's no force in the x direction, so the acceleration in the x direction is 0 for projectile motion, again, if you neglect air resistance. So what that means is that the x component of the velocity is constant. And it's just going to be x over t, basically. They don't show you that. Oh yeah, they kind of do. So there it is. X is equal to Vx times t. So you can have, so this is pretty much the only equation you use for the x component. For the y component, now you have the acceleration is negative 9.8, and they call g, lowercase g, is that constant 9.8, and that's just the acceleration due to gravity when you're sort of near the surface of the Earth. So then, when you know that, these are those equations of constant acceleration, except instead of x, you have y, and instead of a, you now have negative g. So there's a few negative signs that creeped in here, but these are the exact same equations they had before for one-dimensional motion when there was equations of constant acceleration. So, yeah, and then, there's some geometry here, but the way it sort of looks is that if something is flying along here, these purple arrows are the velocity vectors. And then these other two arrows on every dot here are showing just the components of that velocity. And what's interesting is that the blue, the x component, never changes. And I guess up at the top of the path, the purple arrow is the blue arrow. It's all, the whole vector is only in the x direction. But this dashed kind of red vertical arrow, so the y component, changes every second. It decreases until it goes to 0, and then it becomes negative. So that's what it looks like. There's lots of examples, so try to work through the examples. There's this fireworks thing. What are they asking you here? Calculate the height. So they give you the initial speed and an angle. Calculate the height at which the shell explodes. So the way you do that is you say the highest point in any trajectory, called the apex, is reached when Vy equals 0. So that makes sense, right? If you think about this, the y component is positive for a while, then it's negative. Well, so it's going up and then it's going down. So when the y component is 0 of the velocity, that's when you know that it's at its highest point. So you can use one of those equations of constant acceleration and solve for stuff. You're trying to find the height, so you find the final y, I guess. Okay, so by setting that to be 0, and you get something like this, 233 meters. Okay, so I definitely worked through that. There's another one here. It gives you, again, some rock initial speed and angle of the initial velocity. Calculate the time it takes for the rock to follow this path. Oh my goodness. But anyway, I think it's just basically using those equations of constant acceleration, but with the specific, splitting up your y and x component and using same as free fall, right? It's actually very similar to free fall. Oh, and this is a bit advanced. This is where you're saying that, remember, gravity actually is pulling things toward the center of the Earth. So you can imagine if you had a really big trajectory, that gravity would change its direction to be towards the center. So if you launch something farther and farther, there is some speed where you could get it to go right around and hit you in the back of the head. That's called an orbit. Let's take a quick look at this FET animation. The only one I want you to do is just the intro one. And I would just start by taking this cannon, putting it down at 0. And yeah, it's just helpful to kind of show what happens. So there's a projectile. We can increase the initial speed and make it go a little farther. Let's erase the dot there. Whoa, not that far. Shot it right off the screen. Is that a nice one? Yeah. So what we could do is now do that in slow motion, and we will show the velocity vector and the acceleration vector as it's moving. So there you go. So the green vector is velocity, tangent to the path, and the yellow vector is the acceleration. And so what's interesting is that yellow vector, I don't know if you noticed it, is always the same. It's just 9.8, and it's always vertical. There's no x component of the acceleration, it's just this vertical. So that's what gives it this. And then the other thing that you can see, let's actually tilt it up a little bit more. Oop, no. Same. Let's tilt it so it's almost vertical. And send it. So now what happens is that it slows down, the velocity gets less and less. It doesn't quite go to 0 because there's still an x component, but then it speeds up on the way down. So that's one of the, looks like that's a pumpkin here. What else can we, we can throw a human. That's kind of interesting. Let's try that. So that's one of the features of projectile motion, is that when something's going up, it's slowing down. And when something's going down, it's speeding up. But again, with that same oh boy. Watch out! Oh no! Ooh. Oh, he's fine. Okay, good. To finish off chapter 3 on addition of velocities, we're doing relative velocities, section 3.5. So this is just talking about how sometimes there are various objects. And I think the way I'm actually going to introduce it is with my own slides. Now you can use whatever notation you like, but I like to use the following notation trick for vectors. Is when I have the velocity of an object A relative to an object B, I like to write it v subscript AB, meaning the velocity of A relative to B. So B might be the reference frame, or it might be an actual moving object. And what's interesting is that the velocity of B relative to A is always the opposite vector of the velocity of A relative to B. So you'd say VBA equals negative VAB. Okay, so when there's three objects, then you have this really interesting setup here, which is that VAC equals VAB plus VBC. And the way I kind of remember it in my own brain is that I say that these inner subscripts on the sum, the B and the B there, I don't know, kind of cancel each other out, and then they leave the AC. It's just a way of me remembering, but it works a lot. This little trick can help you set up the problem so you don't get confused. For example, I find it a little hard. You got V boat, V river, V tote, total. So what's going on is that there's three objects here. There's the water in the river, which is moving along. There's the ground, like the shore, with the trees on it and stuff. And there's the boat. And so what I would write is I would say, instead of V boat, I would say the velocity of the boat relative to the water. So what's going on is the person who's driving the boat is looking at the shore and just driving it straight, whatever, north or something, straight along the y-axis there. So that's the direction they're steering relative to the water. However, the water has a velocity relative to the ground, which is in the x direction. So the velocity of the boat relative to the ground is this diagonal. So this is the way I like to set up figure 3.30. And then of course you've got the nice vector equation, which is that the velocity of the boat relative to the ground is the velocity of the boat relative to the water plus the velocity of the water relative to the ground. The W's kind of cancel out there. Similar for figure 3.41. Except I would say that there's air. So I would say this velocity of the wind, if you talk about air, ground, and plane, the velocity of the wind is the velocity of the air relative to the ground. And then the plane, if they're steering their plane directly, in the north direction here, then the velocity of the plane relative to the air points north. So what you find there is the velocity of the plane relative to the ground, which is kind of important if you're trying to aim for a particular airport or something like that. So once again, any way you want to set these up is fine with me. This is talking about how velocities are vectors, and so they have components, the x component and the y component. If you have components, you can find the magnitude of a vector with using this Pythagoras. And if you have components, you can find the direction of a vector. So these equations are about when you start with the magnitude and the direction, you can find the components. And these equations are when you start with the components, you can find the magnitude and direction. But either way, you specify a vector. You either have to use the magnitude and the direction, those are two numbers, or you can use Vx and Vy, those are two numbers. So it takes two numbers to specify a vector. This boat in the river, they give you an actual problem, and I would suggest when you set it up, try using my little trick with the notation. I think it probably will help you solve this one. And same with the the wind. I would just say it's the velocity of the air relative to the ground. And then they talk a little bit about relative velocities, which is to say that according to Albert Einstein, all velocities are relative. Okay, so you can't say that something's at rest. Everything is moving in some kind of a reference frame relative to something else. And if you're moving at a constant velocity, all the laws of physics are the same. So, for example, if there is a person on a boat and you think of him in his reference frame, he drops the binoculars and they fall straight down in his reference frame to the bottom of the boat. But the boat might be moving relative to the ground, and then the laws of physics for the binocular are the same. It's just that at the beginning there's an initial horizontal component to the velocity, and so when it drops, it follows this parabolic path. But it still actually lands. It follows the mast, and lands right at the bottom of the mast in both reference frames. So the same things happen, but it looks like a parabola according to the ground. It looks like just dropping straight down according to the guy who's on the boat. And they're just saying here, I guess if you drop a coin while the plane is moving and there's no air resistance, then it would just land right directly below the plane. Obviously, there's a lot of air resistance when you're flying planes, though.